So we stopped in the middle of an important line of an argument. We surveyed the ingredients of the Standard Model, the building blocks of matter, the gluons, the gauge symmetry, and the bosons, the gauge bosons that implement them, the fermions, that is the quarks and leptons, and then finally the Higgs particle. And we surveyed the operating system, which was the kinds of interactions that are of a particularly simple kind, and that those were kinetic energy terms based sort of generalizations of the Maxwell Lagrangian for electromagnetism, but the generalization to Yang-Mills theory, the non-abelian symmetry for the strong and weak, for the SU2 and SU3 groups, and this minimal coupling, changing derivatives into covariant derivatives for the fermions, and the Higgs particle, as far as the kinetic energy is concerned, and then Yukawa type couplings, so fermion bar, fermion Higgs particle, which when the Higgs particle gets a vacuum expectation value, generates mass, and the effective mass and self-interaction of phi to the fourth interaction of the Higgs particle, and that's of the Higgs field, and that's it. That was all the ingredients we looked at. Now I want to argue that that's enough. That not only is it enough, we're sort of stuck with no more than that. This is the result of an analysis of what's possible to realize in a quantum theory of fields, where there are severe problems potentially with ultraviolet fluctuations at very short distances and time scales, that preclude even the existence of theories that you might write down that are more complex. So there's a real restraint. We have to exercise restraint if we're going to get theories out of these ingredients that make any sense. Let's fill in the technical details of how that works. We want to assemble our building blocks, our ingredients of matter, and our ways that they can interact with each other, our operating system, into an action from which we get the equations of motion, the rules of quantization, everything follows from the action. Or another point of view is that when you do quantum mechanics following Feynman in a path integral, the action appears as the weights of the different configurations of the fields. You have to multiply them by e to the I s. So the action is very crucial in what way is the way to formulate the theory. Now, remember, we're using units throughout in which the speed of light and Planck's constant are the units of velocity and action. So c and h bar are 1. And in those units, there's only one kind of parameter left. We can express lengths as inverse masses, masses as masses, energy as masses, and we can translate everything into some power of mass. Our action has to has the same units as Planck's constant. So measured in units of Planck's constant, it's a number. So it has no dimensions of mass. On the other hand, it's gotten by integrating a Lagrangian, or more properly a Lagrangian density, over space-time. So the Lagrangian itself has to have 4 inverse powers of mass, or in other words, 4 inverse powers of length, or in other words, 4 powers of mass as its units. Now, if we look at the kinetic energy terms that we built up, for the gauge bosons, we had 2 derivatives and then 2 field strengths in things like F, or else in the non-abelian case we had either that or a commutator of 2 field strengths. And for those objects squared to build up dimension 4, so for our kinetic energy terms to have mass dimension 4, we have to assign mass dimension 1 to the gauge fields themselves. So to the gauge potentials we assign mass dimension 1. And similarly for the scalar field, for the Higgs particle, we had gradient of phi squared, and gradient of course is 1 over length, so that's a mass, and so to get 4 powers we need the scalar field itself to have mass dimension 1. So the form of our building blocks for the kinetic terms tells us what the mass dimension of the fields that we're dealing with is. And similarly for the fermions, the mass dimension is 3/2. We wrote down only a few simple kinds of interactions that were products of fields with a few derivatives here and there. But that's all there is. Those building blocks, those interactions are all of the interactions that are consistent with the symmetries of the theory, and the restriction that the total mass dimension is equal to or less than 4. So you cannot have, for instance, 4 fermion interactions, psi bar psi, psi bar psi, the sort of thing that appeared in Fermi's old theory of the weak interactions, because that would be mass dimension 6, and that's greater than 4. So if we restrict ourselves to things with mass dimension equal to or less than 4, we've got them all. Now I'm going to argue that we darn well better restrict ourselves to things with mass dimension equal to or less than 4. Otherwise, we're going to have very great difficulty in constructing a consistent theory. Because if we had terms with larger mass dimension in our action, that means this thing, which has to have 0 mass dimension, in terms that have whose operator content has mass dimension equal to or greater than 4, that means the coefficient in front of those things, the sort of numerical or the coefficient, the coupling strength, has to have powers of inverse mass, dimensions of inverse mass. And one way of motivating throwing away such terms, the philosophy of effective field theory, is that we're only constructing a theory that's going to be valid below some reference mass scale squared, and so the coefficients that appear with inverse powers of the mass will have inverse powers of that reference large mass, that cutoff mass, and then so the effects of them will come in with factors of momentum over mass to be compared to the terms that don't have those operators appearing, and so will be small. So that's called an effective theory. An effective low-energy theory is one way of motivating, ignoring the terms with inverse powers of mass in their coupling strength, in their coefficients. Another, which some people think is more old-fashioned, but I think is actually more basic, is to consider what it takes to actually construct the quantum field theories. Quantum field theories have big fluctuations. It's quantum mechanics, and there are fluctuations, and there are modes of very high momentum which fluctuate, and there are lots of them. There's a big phase space at large powers of momentum. So they can, or you might suspect that they are dangerous. And if you actually do calculations using perturbation theory, Feynman graphs, things like that, you find indeed that you get infinities. You're in great danger of getting infinities from the quantum fluctuations. To make sense of the theory and in a constructive way build it up, what you need to do is introduce some kind of regulator, some kind of mass that sets a scale for fluctuations you're going to ignore and try to bring in a controlled way. And if we build in a regulator mass, so we cut off the integrals and then try to take the cutoff, take bring in the very high frequency, very high energy modes gradually, things that appear with positive powers of mass, positive powers of the cutoff, or logarithms, need to be in the theory. Okay, because if we left them out, when we introduce the effects of the high energy modes, they will appear, and because the net dimension is zero or positive when the terms themselves have mass dimension equal to or less than 4, the ones we're keeping, the high frequency modes will induce them with large coefficients, even if we didn't put them in to begin with. So those terms definitely have to be there in order to represent all the content that the theory can produce. On the other hand, if we have those terms with mass dimension equal to or greater than 4, if we have greater than 4, and bring them into the theory and calculate their effects, since they have inverse powers of a mass, when we introduce their effects, feed them back into the theory and calculate the dimensionless quantities, the inverse powers of mass that occur in their coefficients will have to be accompanied by positive powers of the coupling. So those kinds of couplings are called non-renormalizable, the terms that come in with inverse powers of mass, the ones we're not keeping track of, the ones with mass dimension equal to or greater than 4. And this is why we should not have them, why they're dangerous. Okay. So that argument is hand-waving. I was waving my hands, you might have noticed, through the whole argument. But more careful examination, more careful treatment justifies it. So I won't be giving that more careful treatment, but you'll have to trust me that this is the way that is intuitively suggested, is the way to construct quantum field theories that allow the cutoff to all the interactions that the cutoff introduces, all the fluctuations that the cutoff that the high momentum modes induce can be accommodated, and once you've accommodated them, you don't produce infinities anymore. The only infinities that are introduced are things that are already in the theory. Okay, so it's necessary and sufficient to keep the so-called renormalizable interactions, the ones with mass dimension equal to or less than 4, that occur with either dimensionless coefficients or coefficients with positive powers of mass. In fact, if you look over the ingredients of our operating system, it's quite remarkable that all the coefficients are dimensionless, with the lone exception of the coefficient of the h bar squared, the Higgs field squared term. That occurs with, since the Higgs field is mass dimension 1, it occurs with a mass, something with dimensions of mass squared. All the other coefficients, the gauge couplings, the Yukawa couplings, they're all dimension. And the self-couplings of the Higgs field, those are all mass dimension 0. And theta term also is mass dimension 0. Okay, so quantum mechanics resolved, the scholium means commentary. This is something I borrowed from Newton's Principia, and I'm very fond of that style. So quantum mechanics resolved the ultraviolet problem, catastrophe of thermal blackbody radiation. Way back when, the birth of quantum ideas, the problem of blackbody radiation was that in thermal equilibrium, you had many, many modes of high momentum, of high energy, and they had, in fact, in thermal equilibrium, infinities. You got infinities in terms of the specific heat, for instance. But by discretizing the high-frequency modes, kind of thinning out the phase space, Planck got rid of that infinity. However, modern quantum mechanics has not only thermal fluctuations, but quantum fluctuations, and those quantum fluctuations come back and bring it back in those high-frequency modes in a different way, but a way that still has to be treated very, very carefully. So, quantum field theory teeters on the brink of ultraviolet catastrophe even at 0 temperature. And to make it consistent is barely possible, and it's possible if and only if you include the terms with mass dimension equal to or less than 4. Now, this sounds, and is, if you think about it, pretty wild, that we're talking about arbitrarily high frequencies and big fluctuations, quantum fluctuations, in domains of physics that are very hard to explore directly. And how do we know that this isn't a fantasy or a theoretical indulgence? Well, as you'll see, the reality of high-frequency quantum fluctuations is manifested in many concrete physical phenomena, notably including the topological anomalies, which will be the subject of some of this lecture and much of the next one. And also the scaling anomaly of asymptotic freedom. The theory of the strong interaction, if you neglect quark masses, has only a dimension less coupling. And that would mean that it's a scale invariant theory, which means that protons wouldn't have a definite mass, for instance, contrary to experiment. But quantum mechanics saves the day and allows a scale invariant classical theory to become a quantum theory that does have a mass scale. So in both cases, we find that some symmetries of the classical field theory do not survive when you quantize the theory. Okay, so that's why this yoga of constraint, that we allow all the interactions. We have a criterion for which interactions are allowed. The ones that are allowed are the ones that are relatively simple in the precise sense that they have mass dimension equal to or less than 4. And that will let us have the honey of quantum mechanics without getting bitten by infinities. So this is a very precise embodiment of Occam's razor, William of Occam's famous principle that you should choose the simplest solution as the best one. And it's particularly powerful put in the context of the symmetries of the Standard Model, which also highly constrained the possible form of interactions. And this same philosophy can also be taken over in condensed matter physics, and I've just had little pictures of some of the pioneers. Okay, so now with that philosophy in mind, which has a sharp technical justification, I sketched. Let's see in detail its implications for the Standard Model, and in particular what we're aiming at is to show that the general principles of symmetry, and that is the gauge symmetry and the content of the Standard Model, using quantum mechanics and relativity, so we're doing it all in the context of relativistic quantum field theory, that puts powerful constraints on the form of interactions, and in particular will explain almost this weird feature of the world that time reversal symmetry is an approximate property of the laws, but not an exact one. Okay, so if we implement this idea of taking into account all possible dimensions all possible interactions that are of mass dimension equal to or less than 4 and obey the requisite symmetries, we have quite a few things, quite a mess, apparently. Mainly because there are 3 families of all these things. So there are these indices A and B. Remember, this U field was the 3-component field of top, charm, and up quarks, and similarly for the D. So all of these things have 3 family indices. And because of that, in principle, there's nothing that constrains the coefficient of this from having A and B dependence. Okay, so this is recapitulating the ingredients and operating system of the Standard Model. We have these Dirac Lagrangian that leads to the Dirac equation with covariant derivatives here. Remember, left couples to left. And the covariant derivative for the left-handed guys is different from the covariant derivative for the right-handed guys. That's the great discovery of Li and Yang in this language. The weak interaction doublets appear in the left-handed guys, but the right-handed guys are singlets. And then we have the mass term, which involve the Higgs, which is also a doublet. I didn't write out the two components, but that's understood here. And again, we have, in principle, family-dependent indices on all these. So we have quite a mess on the face of it. Even with the yoga of constraint, we still have a sort of messy thing. We would like to simplify it. For instance, what this says, if this is not a diagonal matrix, it means that as quarks move along, they can change from one family to another. Okay. We don't really want that in physics. So how do we argue it away? How do we show that this framework gives a proper description of the world? Okay, so we want to redefine the fields in such a way that the physics becomes clearer. And in particular, we'll see the time reversal properties become much clearer when we clean it up. Okay, so what can we do? Well, we can redefine the fields by unitary transformations. This is very much in the spirit of the little quantum mechanics model that I showed you yesterday. Remember, with 3 components? Not accidentally. It's the same sort of game we're playing here. We're redefining the variables we choose to express the theory in. And so by unitary transformations of these on the family indices, we can diagonalize all the z's. Okay, the z's were Hermitian matrices in order that the Hamiltonian be Hermitian. I talked about the Lagrangian, but it's essentially the same as the Hamiltonian here. So we want that to be Hermitian, and the z's were Hermitian, and Hermitian matrices can be diagonalized by similarity transformations using unitary transformations. So that's what we do here. Okay. So we can take the z's to be diagonal after we choose appropriate combinations of the fields. And if we assume, which we will, although it might be interesting to play with this assumption, but let's assume, because it gives us a good description of the world, that the real entries are positive. They are real, but they don't have to be positive. If they're all positive, we can make them all equal to 1 by rescaling the field, multiplying by a number. Okay, so we redefine what we mean by the symbols so that the z's are just 1. So they're diagonal, and in fact they are the identity matrix. So now we have a somewhat cleaned up structure, no more z's, and just unit coefficients. But we still got these m's to deal with. Okay. And what about that? Well, what's important about those terms is that they're going to generate the masses for the quarks, when the Higgs particle gets a vacuum expectation value. We want the masses also to be a diagonal matrix. Okay. We don't want the particles to be changing, top quarks to be changing into charm quarks and so forth. If we can avoid it, we want to define quarks so that as they just move along, they stay in the same family. Okay, so we want to, or to put it in a more objective way, we want to simplify the mathematical form by redefining the fields we simplify it as much as possible. Okay. From a broad perspective, what we're doing here is saying that we have general principles of a high level of abstraction, gauge symmetry, and relativity and quantum mechanics, that we squeeze as much as possible, and the yoga of restraint, we squeeze it as hard as possible to get its physical content clear, and then we see if it matches the world. Okay, so it's kind of an inversion of the traditional model of empirical science, where you start with a lot of data and then try to model it. Here, by a process of accumulating experience, and experiment still gets the final word, but now we're saying that we can understand the structure of the world, which is highly described by the standard model. We can derive it from these general principles. And so we're going to be focusing on time reversal symmetry, but the whole picture is absolutely remarkable, that you get from these very general principles down to a minutely detailed description of the world as it actually exists. All right, so let's do it. So we want to simplify those m's like we simplified the z's. Now the m's don't have to be Hermitian. Because this thing, when you take the Hermitian conjugate, doesn't go into itself. So when you have the Hermitian conjugate, you get the Hermitian conjugate of this matrix, too. So it doesn't have to be Hermitian. So we can't diagonalize it in quite the same way, but in linear algebra, it's demonstrated that you can diagonalize an arbitrary matrix if you have different unitary transformations on the two sides that you can adjust. Okay? So if we want to invoke this theorem, we need to make unitary transformations on UL, DL, UR, and dr independently, on those three component vectors, all independently. By the way, I didn't mention it, I should have. I've been writing only the quark fields. There's a similar story for the leptons, very similar, but and it's not important for time reversal so much, so in the interest of time, I will just do the quark. Okay. Now, of course, when we do these transformations, we have to make sure that they're consistent with what we did before. We've worked very hard to make those kinetic terms as simple as possible, and we don't want to undo that work. Now, and it's almost, but not quite, possible to make independent unitary transformations that we need in order to simplify the mass matrices without undoing what we did before. But not quite, because, well, unfortunately, it's hard for me to navigate on this on these slides. But let's. Yeah, so it's good enough. You see here, in order to have the doublet structure for the weak interaction represented, we have to have UL and DL coming together. So we don't get to make separate rotations on UL and DL without messing up the diagonal structure here. Okay. So we have to pay careful attention to the effect of making this simplification that we do to simplify the mass terms. What does that do to the kinetic terms that we've already massaged? Okay. So for the mass terms, we make relative rotation. We have to make independent rotations on the ULs and the DLs. But that interferes with the diagonal structure of that left-handed term, which had them in a doublet. Okay, we'll analyze the consequence of that momentarily, but let's pause to emphasize that up to that issue, all the terms in our standardized action now, the kinetic energies, the diagonal mass terms, and the Higgs terms, all of them are of a form where we know how to define a time reversal operation explicitly. Okay, the sort of thing we discussed last time. Basically complex conjugation plus a little extra massaging when you have spin or Dirac equation. So we've come a long way in seeing how time reversal symmetry emerges as a result of deeper principles. But we're not quite done because we haven't analyzed the consequence of this mismatch between what we want to do on M and the doublet structure of the kinetic term, and we haven't addressed the theta term either. Okay. Now, the first of those loose ends is the subject of the Kobayashi-Muskawa theory. And so, who cares if you make relative rotations between left-handed up quarks and left-handed down quarks, or the left up and down in the generalized sense, those triplets? Well, W bosons care, because W bosons change up type into down type. That's the reflection of that's why we put them in a doublet, because they're things that connect them. The gate. Okay, so let's isolate those terms, the dangerous terms, the ones that make the doublet into a doublet. They look like this, and we've made a relative rotation. So there's a unitary. It used to be. It was started out being diagonal but by diagonalizing the mass matrix, we may have to introduce a relative unitary transformation, which here we called S. So the dangerous terms are exactly these. And our straightforward implementation of time reversal which involved complex conjugation, as well as the operations on gamma matrices, doesn't leave this invariant. Doesn't leave this thing invariant. In fact, it changes. I'll leave this as an exercise of this for you to show this, but it should be plausible based on the fact that we complex conjugated things to implement time reversal symmetry, that our implementation of a potential time reversal symmetry in this, applied to this term, takes S into S star. So if S is not equal to S star, very much like in that simple quantum mechanical model I showed you, not accidentally, we'll get violations of time reversal symmetry. So, as it stands, S is just a unitary matrix. So there are a 3 by 3 unitary matrix if we have 3 families. So there are lots of complex numbers in it. Even if we had just 2 families, there would be complex numbers in the unitary matrix. But we still have some freedom left, without messing up anything we've done before, to change the definition of the fields and change them in a way as to make their symmetry properties as clear as possible. So, without disturbing anything we did before, the canonical kinetic terms we derived, or the fact that the mass matrix is real and diagonal, what we can still do is make phase rotations on, just phase rotations, not unitary transformations, just phase rotations on the left and right-handed versions of any quark field. Okay? Because that leaves the masses invariant, leaves the kinetic energy invariant. That's perfectly okay. That leaves the canonical form unchanged. So, if you think about it, the S here, this matrix S, which is not the same as an S matrix, it's just the matrix S, because you could, which connects up-type quarks to down-type quarks, if you can make phase rotations on them separately, you can use that to make these guys real. You can use that freedom to make these guys real. So, by rotating the up-type quarks separately, you can make whatever you had before, you can make them real, and then you have 2 more phases for down-type quarks. You can make these guys real. And then you're stuck. Okay? So S is a unitary matrix with all that stuff real, but it still can have a complex number. You can still violate time reversal. It's barely possible. There's a unique complex number that occurs, a unique phase. Why? Because there are 4 entries here, but remember it's a unitary matrix. So the Hermitian product of the rows has to vanish. Different rows has to vanish. Okay, so the relative phase between this and this is fixed by that condition. And then the third row is basically the cross product of the first 2. So there's only one phase that occurs in this. So you get a 1-parameter theory of time reversal violation. That's supposed to govern all the time reversal violation in the world. It occurs only in the weak interaction because it involves the W's. And it's a particularly obscure corner of the weak interaction because if you had only 2 families, then you could eliminate the time reversal symmetry altogether. The theory would automatically conserve time reversal. This was the big realization of Kobayashi and Miskawa. So they predicted, at the time it wasn't clear, it wasn't known at all, that there was a third family of quarks and leptons. So they predicted it, and they predicted a particular form for T violation in the heavy quark sector that they predicted existed, and it has been very successful. The third family was found very soon after they made this kind of prediction, and it's been the one parameter theory of T symmetry has been amply vindicated when people studied the decays of heavy quarks, where you have many access to many of these interactions of the W bosons that you didn't have before and could measure in great detail. Okay, so that's a tremendous triumph. But dramatic pause, sorry. We have another potential source of T violation, namely the theta term. Now, formally, the theta terms are total derivatives. They don't appear in the classical equations of motion. This is more or less obvious for the electromagnetic term, where it's FF dual, or epsilon times F times F. That means, if you remember that F is d mu a nu minus d nu a mu, you can take a derivative outside of the epsilon symbol, and that's the theta term is a total derivative. Or you can show directly, if you want to do a nice exercise in electromagnetism and the use of vector potentials, that E dot B is a total four derivative. It's also true, although less obvious, in the non-abelian case. Sorry, this doesn't work like my computer, I'm afraid. Okay. It's the opposite. We're on the opposite sides of the Earth. Okay. So, they have no effect classically, with an asterisk. I'll come back to the asterisk. And that means they have no effect to all orders in perturbation theory. They don't appear in Feynman graphs specifically. Because Feynman graphs are generated from the classical theory. The asterisk is that if you consider fields that extend to infinity, or if you're Lagrangian, applies to a finite region of space, so you can't throw away the surface terms, then it does affect classical physics. And we'll see examples of that soon. So, unfortunately, maybe, although I don't think Kobayashi and Miskawa should give back their medals for this, the full story is more complicated. The theta term, in fact, is not something you can neglect. When you do the quantum theory, the theta term is physically significant, and those terms are potentially a source of T violation. We thought we had slayed the dragon, but we hadn't. Okay, all the general principles still leave one potential source of T violation that's not under control. So the story is more complicated. As we'll see, that's a good thing. Maybe a very good thing. So, two deep and deeply related aspects of quantum field theory come into play when we talk about the theta term, topology and anomalies, and we'll discuss them next time, meaning this time. We'll start the discussion as it's a key part of the motivation for introducing axions and potentially solving the dark matter problem. Okay, so now can we get to this other? And I showed you this roadmap yesterday, so I won't repeat it.
It takes several seconds to...
Okay. Okay, well, here's that roadmap again. The argument is, I think, it's a chain with a logical chain that has many links. The links are very strong, but it's maybe difficult at first sight to see the big picture. So this diagram, I hope, will help you. We're going to show that QCD seems to have a problem if you just treat it on the basis of what the classical version of QCD suggests. In fact, it seems to have more symmetry than is manifested in the world. But the effects of instantons and topological interactions, so-called anomalies, we reduce the symmetry and get rid of that problem. So that shows that these effects are beneficial in a way and absolutely essential if QCD is going to describe the world correctly. But on the other hand, the very same effects show that the theta term has physical significance and gives us the big problem of this extra source of T violation, this potential extra source of T violation that is not explained by the Kobayashi-Maskawa theory or, more generally, the structure of the standard model and symmetry restrictions, this beautiful picture that almost resolves the question of why the fundamental laws have approximate but not exact time reversal symmetry. So we'll make a start on this, and then I'll at a logical time, I'll draw the line. Okay, so let's start talking about this theta term in QCD. We already made this point. Okay, so this is going. First, we're going to survey it sort of broadly, and then we'll get down to the nitty-gritty technical details that are really very beautiful and profound, but not necessarily easy to grasp at first sight. So we've analyzed transformations of the standard model Lagrangian, and its structure. Now we want to see what that gives, what it means when you turn it into a quantum theory. And there are different ways of doing that, changing the classical theory into a quantum theory, but maybe the way that's most intuitive, and the one that certainly is very convenient for the things we're going to be doing, is the Feynman method, which is you go to the quantum theory by integrating over all possible classical configurations. So you say the classical fields could have fluctuated in different ways, and you have to add them up. And of course, you need a rule for adding them up, and the rule is you use exponential of the action times I. Now, that's very bold, because what does it mean to integrate over all possible field configurations? You're integrating over big function spaces. Okay, this is not your grandmother's integral. Okay, it's a really big. It's not Isaac Newton's integral. or any respectable mathematician's integral. Really, it's a big space. And how do you do that? This is another manifestation, if you like. There are many degrees of freedom in these function spaces, including very high frequency fluctuations in particular. The fields may not be very smooth when you integrate on them, over them, and that's where the ultraviolet divergences come from. So there are significant issues around the measure of the integral and the kind of fields that it allows to contribute. And in the context of the theta term, in the classical theory, we argue that it's not significant because it's a total derivative. But if it's the total derivative of something that's singular, we can get surface terms. Okay, so if the fields that we integrate over have to include singularities of the right kind, then a term which formally looks like a covariant, looks like a derivative, that is not giving zero in the integral of the action, so not giving zero in the weight of the quantum mechanical measure. So in other words, those fields appear, and the theta term has a physical effect on them. So here's how it manifests specifically in the context of the theta term. We have the kinetic energy kind of term is square of the field strength. And in order for the measure to be finite, we want the square of the field strength to be finite. Okay? Now, there are some technicalities really to do this. I should talk about going to imaginary time and using the Euclidean theory, but I'm not going to do that. These lectures would develop infinities if I started to try to do that kind of thing. Okay. So let's take it that we need to concentrate on fields such that the square of the field strengths are finite. What does this say about not when we have the square of the field strength, but when we have g mu nu times epsilon mu nu, epsilon g mu nu? Well, that theta-like term was the partial derivative, was the derivative of some k mu, and when we do an integration by parts, we get the integral of k mu over potentially places where it becomes singular. Okay, when we can't get rid of the surface terms. But that has to happen in such a way that at the singularity, g mu nu goes to 0. Because otherwise we're going to get an infinity here, and we don't want the infinity there. So g mu nu has to be regular, but if we're going to get a contribution to the, if theta is going to have physical significance, if we're going to get a contribution from the integration by parts, we need a singularity here. That can occur because in a non-abelian theory, g mu nu contains both d mu a nu and a mu a nu, contains both derivative parts and covariant derivative parts, commutator parts, and those can cancel in g mu nu, but not necessarily in k mu. So in principle, you can get, and in fact, in practice, you get contributions where g mu nu goes to 0, but this thing does not go to 0. In fact, I mean, its surface integral doesn't go to 0. Now, you may be suspicious of that because if the field strength goes to 0, we usually say that indicates that it's a pure gauge transformation, that it's physically trivial. Okay, this is where things like the Aharonov-Bohm effect comes into play. But at a classical level, this indicates, at least locally, it indicates that the field strength is a pure gauge. If the field strength goes to 0, that we can make a gauge transformation locally that sets the potential to 0. However, that's only locally. We can't do it globally, as the Aharonov-Bohm effect teaches us in a very simple form. It's also true in this non-abelian context. And we can have fields that are locally trivial, locally equal to gauge transformations, but not globally. And that means we can pick up, if that happens, we can pick up these surface terms. Okay. Yeah. It's d mu k mu equals epsilon gg, trace of epsilon gg. So it's the thing that occurs in the theta term. I should have written that. So, is there a blackboard here? Maybe no. Well, yes, there is a whiteboard. It's good enough. So the thing that appears in the theta term, this, is proportional to, it's a total derivative, so it's proportional to d mu k mu. That's the definition of k mu. So, by definition, that's what k mu is. Okay.
Okay, thank you so much. That makes the thing clear.
Okay. So, these effects don't occur for small values of the potential, of the field potential, the a mu's, because they can only occur if you have cancellation between a mu and commutator terms. So they only occur for large fields, which means they don't occur in perturbation theory. Also, they are topological because they are effects that occur because there's a difference between local structure. Locally, you can make a gauge transformation to make a mu goes to 0, but not globally. So there's a topological aspect to it. And what that turns into is, in terms of physical amplitudes, is that the contributions of the theta term are periodic because the topology has a discreteness to it, like this, and also that they're non-perturbative, so they appear like that in explicit in model calculations. Okay, so those arguments were somewhat heuristic, but we'll give very much more rigorous arguments next time, and numerical calculations confirm. See, in QCD we can do numerical calculations on supercomputers that are remarkably powerful and precise, and we can check things like this. We can confirm, and it has been confirmed, with no uncontrolled approximations, that the angle theta is a genuine parameter of QCD. If you change theta, physics changes. So even though it's classically not a parameter, it is a parameter in the quantum theory. And it violates time reversal if theta is not at a special value. So time reversal changes theta into theta. We showed that last time that epsilon trace GG is odd under time reversal. So in other words, time reversal changes the sign of theta. And that means, because theta is periodic, that's why it's conveniently called an angle, we have time reversal only in two cases: theta equals 0 or theta equals pi, modulo 2 pi, and other. Changing it by 2 pi has no physical effect, so those are the only two cases, really. So the bottom line of all this, the takeaway message, is that there's a second consistent t-violating parameter different from the one contemplated by Kobayashi and Maskawa. It governs interactions of color gluons with each other in QCD. And there's a potential way that those interactions can violate time reversal symmetry. That's consistent with all general principles. Is it manifested in the world? Okay. We've had this marvelous match so far between the things that are allowed by general principles, not only for time reversal, but everything in the standard model. We have every single parameter is something that we use in the description of nature, and there are no other parameters in the description of nature that don't appear in this canonical form of the standard model. What about this one? Well, this one doesn't appear. It's allowed to appear, but it doesn't appear. Empirically, one can do very sensitive measurements of whether there is time reversal violation of this new kind. It will induce electric dipole moments of the neutron, and you can calculate the size of those coefficients, size of those effects, and when you compare with experiment, I'll discuss this a bit more next time, you find that the absolute value of theta, which has every reason to be of order unity by dimensional analysis, is less than 10 to the minus 10th. So, the bottom line, and this I think will be a logical place to stop for today, we've come a long way towards tracing the observed pattern of time reversal violation, of time reversal symmetry and its small breaking in the world to deeper principles. But our work is not quite done. There's one loose end that still needs to be tied up. We have to understand in a satisfactory way why there's this terribly small number, 10 to the minus 10th, that governs a potential time reversal violating interaction that does not occur. And as I said, that's a good place to stop. Thank you. So you have a lot to chew over until we start next time. Yeah.
So the time is open to questions.
Yeah.
Your question.
Hi, Professor. Could I ask, in your talk, do you mean that time violation of time reversal symmetry is the natural result of some theory with some constraints?
Yes. So that's, I hope I was able to show in honest detail, if you take the general principles that are embodied in quantum field theory and the particular content of the world, the quarks and gauge symmetries that we actually have, you find that you get powerful restrictions on the possible forms of interactions. Okay, if you didn't know there was such a thing as an up quark and a down quark and so forth, or what their properties were, and just knew the general structure, you'd manipulate according to these principles, you'd find something that has the exact properties of what is seen for those objects we call by those names in the world. That's the big statement. And among them, in particular, you find that there's one parameter, this one phase, that gives a time reversal violating interaction, and it matches exactly the pattern of time reversal violation that's seen in the world. So it explains the original discovery by Fitch and Cronin back in 1964, and a host of later observations in the study of decays of B mesons and things like that.
Thank you. So I just curious about why this constraint is more important than the time reversal symmetry.
Well, because it's true. The time reversal symmetry is not true. If it were true, if it were an exact principle, then we could build on it. But the fact that it's almost true but not quite true means we have something to explain, right? So, yeah.
Okay. And the second question, you mentioned there is some singularity, and when build a theory, and I just wonder, is the type of singularity influence the result?
Yes. Oh, yes. The study of what kinds of singularities are allowed is a very profound theme that occurs in different ways in physics. Perhaps the original appearance of this kind of thing was Dirac's analysis of magnetic monopoles in quantum theory. Classically, there's nothing wrong with having magnetic monopoles. It's a big mystery why you don't have them, in fact. You can perfectly well add them to Maxwell's equations, and they become, in fact, the equations become more symmetric.
Okay, thank you.
But in quantum mechanics, you can't deal directly with Maxwell's equations. You have to introduce potentials to do, you have to have a Hamiltonian formulation, which means you have to introduce vector potentials and so forth. And in order to accommodate del dot B, del cross B has to have a singularity. And what Dirac showed is that certain kinds of singularities are allowed in quantum mechanics because they're invisible to other quantum mechanical variables. So he made it plausible that quantum mechanics would allow magnetic monopoles, but only if their strength, the strength of the magnetic monopole were a topologically determined value. So that was Dirac's contribution, and it's similar things now are invoked in different parts of condensed matter physics and very much in this question of the theta term and its influence. That's where you have to include to see the physical significance of the theta term, that it has physical significance, you have to allow topologically non-trivial gauge fields. For the reason I showed you, you have to have things that have g squared finite, but this k not being something you can not finite, because it gives it, even for a small surface, it gives a non-zero contribution. It's a surface term, but it's singular enough that it survives.
Okay, thank you.
Yeah. Yes.
Thank you. So my question is basically like this. In your talk, you've scrutinized in detail the different building blocks of the interacting relativistic field theory.
Yes.
And you found that the theta term could be a source of T violation.
Yes.
If we have 3 or more generations of quarks and leptons.
No, even if you didn't have 3 generations, even if you had no generations at all, the theta term, it's an interaction purely among gluons. So it doesn't require the complexities of Kobayashi-Maskawa theory.
Yes.
It requires a different kind of complexity, namely the complexities of quantum field theory and topology. But
do we have other possibilities and mechanisms with which we are able to seek time reversal?
There are no other. These are the only 2 that are consistent with the yoga of constraint that I discussed. So these are the only 2 that are allowed if you put in the constraints of having a quantum field theory that makes sense,
yes,
that has the symmetries of relativity, quantum mechanics, and the gauge structure of the particles in the standard model.
Okay.
Yeah.
Okay. Thank you.
So that's it. That's it. And so we have 2 possible interactions. One of them is seen, and it was a great triumph. The other isn't there. So it's a real that's the puzzle. Okay.
Hi, Professor. I have a question that in the last part of your discussion, you introduced the theta term from the gluon kinetic term. So
yeah.
Why there is no theta term for the other gauge boson?
There is. There are 3 theta terms.
So why they are trivial?
They're not trivial. They just have very tiny effects.
You mean their effect? Maybe they are also CP violation, time violation.
They would also violate time reversal, but their experimental consequences are unobservable, as a practical matter, unobservable.
Much smaller than the.
Much smaller than. Yeah.
But actually, it should be have the T violation cannot.
Yes, they could be an additional source of T violation, but we don't know experimentally one way or the other if that's there.
Okay. Another question.
Good question. Very good question.
Another question is that so actually the star model also have we know that the phase in 3 generation also has the T violation, but
yes.
I think maybe it also have contribution to the electric dipole moment. So
yes, it does, but that also is very numerically small, because because the 3rd generation is important. That means you have to somehow involve the 3rd generation. If you're looking for contributions to dipole moments, it's very indirect, and it turns out to be several orders of magnitude smaller than the experimental limits.
So why why people also assume the theta is large enough so that it's much larger than this effect. So maybe theta is also very small.
Well, it is very small.
Much more.
It's very small.
No, it's constrained on 10 to 10. Maybe it's much small, so that there is that possible that this T violation is somehow similar to the, so it's almost the same to the generation T violation. Is that possible? So there are two effects is comparable. If theta is so...
well, they're very different, so it's hard. It's like comparing apples and oranges, as they say.
But
theta is a pure number.
Oh, okay.
And the principles of dimensional analysis would suggest when you have a pure number, unless you have some reason to think otherwise, it should be 1. Or 10th might not be so disturbing. Even 1 in 100 might not be so disturbing. But 10 to the minus 10th, that needs a qualitative explanation. And so that's going to be the story we'll unfold next week.
Okay, maybe next week. Yeah, thank you.
All right. Yeah.
Hi, Professor Wilczek. Thanks for your nice talk. And so my question is, so you mentioned that in the standard model, the coupling coefficients, except the mass terms, are all dimensionless.
Yes.
I remember. So why is that? Is that a coincidence or?
No, it's not a coincidence. It's a consequence. This was no coincidence. I showed you all the possibilities.
Oh, okay.
So it's a consequence of what kinds of particles there exist, and the symmetry, the gauge symmetries. So the only possible interactions you can have are dimension 4, mass dimension 4, so they have dimensionless coefficients, with the sole exception of the Higgs mass, the mass term involving the scalar field. But that's
okay.
It's just, yeah, so I don't know if you want to call it a coincidence, it's a fact.
So it's just based on the symmetry,
Yes.
field theory.
Yes.
Okay, thank you.
Right.
Hi, Frank. I have a question. We know that inside event horizon of a black hole, the temporal coordinate and the spatial coordinate exchange roles. So
Yes.
R becomes T and T becomes R.
Yeah.
So does everything we know about time reversal still hold true inside the event horizon of the black hole? And in particular, how do we do time reversal in this case? Because there is no minus R here.
Yeah, well, that's an interesting question. I haven't thought about it. The equations are unambiguous, but I haven't thought about what their implications are. I have enough to worry about outside this black hole. I know, but I know a lot of my colleagues are obsessed by what's going on inside black holes. I guess I'm maybe less obsessed than most. All right. Yeah.
Hi, Frank.
Yes.
So you have mentioned that in a Lagrangian, we only consider the terms less than mass dimension 4, right?
Yes.
So,
equal to or less than 4.
Yeah, I'm curious. So if we could have terms with fractional mass dimension.
Well, not within the framework of local interactions.
Uh-huh.
So yeah, if you included things like fractional derivatives or square roots of fields, things like, but those have big problems.
Okay.
So no is the basic answer.
Yeah.
There is one thing I could have mentioned. There's another kind of interaction that has mass dimension 0, namely the operator 1, right? Just that has no fields at all. That's called cosmological term. And it's very puzzling also why that is so small in nature. That's a mass density of empty space. So it doesn't represent any interaction of particles in the way, but it's a property of space and it affects gravity. So I wanted to talk about time reversal, and that's kind of irrelevant, but to that. But it's another dimension. It's a low dimension operator, namely the operator 1. And so that's the only other thing that's consistent with all the general principles.
Yes, I see. Thank you.
Okay.
Other questions?
Frank, I will ask you a question about the renormalization and the
Yes.
non-renormalizability. We have, from your lecture, we know that from the mathematical structures, we could see clearly the difference between these two. But I would like to ask if there are more information we could get from these two properties. For example, for the four-fermion interactions, we know that it is non-renormalizable.
Yes.
And that indicates there are more higher energy theories that could describe it, and that theory turned out to be renormalizable.
Yes.
And could we have a general statement that all the non-renormalizable theories have something a little bit higher energy theories?
Yeah. So this is known in the literature as the question of whether theories have ultraviolet completions. Mm-hmm. Whether a theory that's non-renormalizable might be a low energy limit of a theory that is renormalizable, or at least that you can construct. And I'm not sure the exact status of the understanding of that. Many theories certainly can have ultraviolet completions, including the Fermi theory of the weak interaction, which is completed by the Standard Model. But I think there are other things that can't be embedded consistently within a quantum field theory. I should really add, in honesty, that my discussion of renormalization theory was pretty heuristic, and I didn't tell you anything that's false, but a full picture would be more complicated because. For instance, if in lower dimensions than 4, you can have non-renormalizable interactions, and the theory appears to be very problematic, but actually, when you solve the theory more rigorously, non-perturbatively, you can construct such theories. Also, if you have supersymmetry, that makes ultraviolet divergences less nasty. And so if you have supersymmetry, you can sometimes relax these constraints. But if you don't have, in 4 dimensions without special symmetries, you're basically stuck with mass dimension equal to less than 4. Yeah.
I see.
Mm-hmm.
Any other question?
All right then. Okay. Thank you.
So we recorded all lectures and we put the movies on the internet. We also added these transcripts in the movie, both in Chinese and English. So if you want to know more, then you can just scan this QR code. Then you can watch these lectures in the past several days. Yeah, thank you.